we will discuss energy relation in a coupled oscillation. It is a long derivation, so we will cover it into two parts. In the first part, we will discuss about the coupled oscillations, in which we will take two masses which are connected with the help of three springs having different mass magnitude, and the springs have different spring factor or spring constant. And after that we will find out their frequencies and find out what type of the relation in between the amplitudes of the masses when they are displaced from their mean position or they undergo the simple harmonic motion. Let us consider our system. It is in rest, and the system consists of two masses, and let us consider this is our ground and the reference frame, and this is the mass first, which is represented with the help of ma, and this have given a notation of a. And the another mass that is different from the first mass, it is denoted by mb, and it is also denoted by b, that is the b mass, B particle or B object, and the first A mass or MA is connected with a spring having a spring constant K1, and the second mass, which is B or the particle B, is connected with a spring K2, and both the springs are attached with a coupled spring K3. This K3 will couple the motion of the first particle to the second particle. Without K3 there is no coupling, there should be no coupling. And when we apply some force and the particle, let us consider the particle A get displaced from its mean position. Now the particle moves with a displacement of psi A when the applied force is given to the particle A, and the spring xk, the first spring get an expansion. Similarly, let us consider in the same direction in the right hand side, the spring b is also displaced with a displacement of psi b, and due to which the spring k2, the second spring, undergo the compression, and the compression and the expansion is done due to the coupled spring, that is K3 spring. If the K3 spring is absent, then we can write the simple harmonic motion for the A particle like this, that is mass into acceleration is equal to the restoring force, and in the first case the restoring force is given by minus k times the spring constant of displacement, and the spring constant of the first particle. If this spring is absent, then we can write the simple harmonic motion of this system, this very system having a particle A. But due to the spring K3, there is a change in the motion, or there is a applied force on the first particle also, and it is due to the coupling of K3, that is the connecting or the coupled spring, we will have an extra factor which will enhance the motion of our first particle. Similarly, if the coupled spring and this common spring is absent, we can write the expression for the equation of motion for the second particle like this: mb psi b double dot, that is the acceleration. If we differentiate the displacement two times with respect to time, differentiating with respect to time, then we will get acceleration. And if this coupled spring is absent, we will give this equation of motion for the second spring, that is our B spring. But due to the presence of K3, there is a change in the motion of the second particle, and it is given like this: K3 psi b minus psi a. It means this extra factor is due to the coupling effect. Now, if we will solve out both these equation, from equation number 1, we will get m a psi b psi a double dot is equal to, just open this bracket and collect the psi a terms and just differentiate the psi b terms from the psi a. We will get minus k1 with minus k3, and we will take psi a as common. We will have k1 plus k3 times of psi a plus k3 times of psi b. We will get equation number 3 from equation number 1, and from equation number 2 we will get equation number 4 like this: mb psi b. Just we are doing the same as we have done in the previous equation. We will collect the psi b terms at one hand and psi a terms on the another. We will get k2 plus k3 times of psi b plus k3 times of psi a, and this is our fourth equation. These equations are just didn't by these equation we can't find out whether they are simple harmonic motions or what type of motions are they going to give us. To reduce this equation, we are just reducing using some reduced coordinates. Let us consider there is a coordinate x, and this coordinate has a relation with psi a as under root of ma psi a. Similarly, we are taking another reduced coordinate y, and this is given as under root mb psi b. These assumptions of reduced coordinate will change our equation to simple harmonic motions. We will see in our further calculations. Just put the values of psi a and psi b in the terms of x and ma, x, y, and ma and mb. What we will get? We have psi a is equal to x upon under root ma from our x terms, and from this term y is equal to under root mb psi b, we will get psi b is equal to y upon under root mb. If we differentiate psi a one time with respect to time, then under root ma undergo no differentiation, no change with respect to time. Similarly, this factor is also constant, only and x and y will vary. We will have psi a dot is equal to x dot under root ma, and similarly psi b dot is equal to y dot, that is the velocity of the first particle and the velocity of the second particle in the terms of x and y, that these are the reduced coordinates. We will get this again differentiating these two. We will get psi a double dot, that is the acceleration of the first particle, x double dot under root ma is constant term, so dot will undergo differentiation. Similarly, we will get the value of psi b double dot, that is the acceleration of the second particle. Now, substituting all these equations in equation number 3 and 4, what will we get? We will have, using equation number 3, if we put all these getting values in equation number 3, what will we get? We will have m a, and instead of psi a double dot we are getting x double dot under root m a, and this is equal to minus k1 plus k3 times of psi a, and instead of psi a we are putting the value, that is x upon under root m a plus k3 psi b, and instead of psi b we are using y divided by under root mb. This is our equation number 5, which we obtained from equation number 3. Just what we had did, uh, instead of psi a we are putting the terms x double dot, and instead of psi a we are again in terms of x we are using, and instead of psi b we are using the terms in y. And by rearranging all these terms, we will have some equation in the terms of x double dot, and what we will get, we will have x double dot is equal to, just uh, moving these ma and under root ma towards the right hand side, we will get minus k1 plus k3 x and under root ma is cancelled by this, and we will get factor ma in the denominator of the first term plus k3, and in here what will we get, y divided by under root mb, we get here in the numerator, and ma we will get in the denominator, and on outing the all these terms, we get k3 divided by under root ma and under root mb. These are the terms which we get from equation number 5th by rearranging all the terms. Let us consider this is equation number 6th. Similarly, if we use equation number 4, this is our equation number 4, and using the value of y here in the terms of just exchanging the psi b and psi in the terms of x and y, we will get again the equation number, the using equation number 4, what will we get? We will have y double dot is equal to minus, and this is with k2 plus k3 divided by mb, and with positive sign again we will get k3. Here we will have x divided by under root MAMB, and here we will get y. These are the terms which we will get from the equation 3rd and 4th. So we have equation number 6 and equation number 7. These expressions are just a long expression in the terms of k and y. We are just substituting some constant values here, just replacing these terms with some constants. Let us consider we have taken this term as a11, that is a11 is equal to k1 plus k3. These are all constant values. K1 is a spring factor, spring constant for the first spring. K3 is also a constant. If you add a constant to constant, you will get a constant. Again, you are dividing the constant with a constant, you are getting again a constant, and we are just substituting the value of these constants as a constant, and here we are representing it with a11. Similarly, this constant we are representing it with by a22, and here a22 is given by k2 plus k3 divided by mb. Similarly, this k3 divided by under root ma mb also representing and another constant. And in first case where we represent this term as a11, we are representing this term as a12, and in this case here this term is represented by a22, and this term here we are representing by a21. It means a12 is equal to a21, just in the form of matrices element we are using these notations. A12 is equal to a21. This term we are representing as a12, and this term we are representing as a21, and both are equal to, we are taking the negative sign for our convenience, under root ma and mb. Then this equation will become x double dot is equal to minus a11, and now here we will get minus a12y. Similarly, here we get minus a22 minus a21x. So just we are reassembling our equation by putting these constants a11 or some matrices element here. We are just using our reduced equation as x double dot is equal to minus a11x minus a12y. Similarly, we get equation y double dot is equal to minus a22y minus a21x. Let us consider these are equation number 8, and this is our equation number 9. These are the reduced forms of our equation which we derived from a system connected, having two masses, different masses connected with three springs. These these values a11 and a22, what a11 is representing? A11 is representing k1 plus k3 divided by mb, that is the spring constant divided by inertia factor. And we know that spring constant and inertia factor that comes in the formula of the angular velocity. Similarly, what is a22? A22 here is, we know that this is k2 plus k3 divided by m B. Here this is MA and here this is MB, that is mass of first particle and mass of the second particle. Again, we very well know that if we want to find out the general formula for the angular velocity, we know that we get here the spring factor, that is the spring constant. Here we will get the inertia factor or inertial factor, that is our mass. Here something look like this. If we take the under root of these two factors, it means these two factors are representing somewhat angular velocity. We will find out what type of angular velocity they are giving to us from our calculations. If we put a condition that the first particle is moving, it means first particle is showing a displacement, and at that time another particle, the second particle, is showing no displacement. It means it is clamped or it is just restricted by its motion. What will happen in this case? We will get the angular velocity, that is a11, which is given by omega a is equal to under root k1 plus k3 divided by ma. We can find out this formula with the help of our equation number 3 also. This is our equation number 3, and with the help of our equation number 3, we can easily find out what will happen if the psi b factor becomes equal to 0. Let us consider the second particle is not showing any displacement. If second particle is not showing any displacement, what will you get? You will get the acceleration is equal to k1 plus k3 divided by ma and times of, that is psi a, and this value is nothing, it is your acceleration. This is your angular velocity square, and here we will get omega a is equal to k1 plus k3 divided by ma. Just remind yourself, in the form simple harmonic motion, we will have a relation that in between the acceleration and the displacement. If a is the acceleration of the simple harmonic motion and y is the displacement and omega is the angular velocity, this is the relation in between the in between the acceleration, displacement and angular velocity. Here we are getting the same from here equation number 3. If we put psi b is equal to 0, this factor is going to be 0. This becomes psi a, that is displacement, and this is psi a double dot, this is acceleration. What will you get from this equation? You will get, that is psi a double dot is equal to minus k1 plus k3 divided by ma into psi a times. This is our relation. If you just correspond this relation with this, what will you see? This is acceleration, this is also acceleration, this is displacement, this is also displacement. It means this term is indicating omega square. If this is omega square, then what is omega? Omega is under root of this term, and we are here talking about the same thing. When the second particle is in rest and the first particle is showing a displacement of psi a, we are getting the first particle is moving with this angular velocity. Similarly, we can find out for the another one. If we just vice versa the condition, now we are substituting psi a is equal to 0. It means the first particle is not in motion and the second particle have a displacement of psi b. Then what will be the angular velocity? Now again use your equation number 4. From equation number 4, what will you get if you put psi a is equal to 0? You will get this term is equal to 0. If this term is equal to 0, then what will be the value of psi b double dot? You will get psi b double dot is equal to minus k2 plus k3 times of psi b divided by mb. And again, you just evaluate what this equation is correspond. If we just equate the equation psi b double dot is equal to minus k2 plus k3 times psi b divided by mb, with our previous equation, that is a is equal to minus omega square y, we will find out that this omega square is nothing, it is k2 plus k3 divided by mb. So when the displacement of the second particle is 0 and first particle is 0 and the particle second is displaced by displacement of psi b, then the second particle will move with an angular velocity or angular frequency of under root k2 plus k3 divided by mb. Hence these are the two frequencies by which the particles move when one particle is in rest and other is in motion. Now we will deal about their simple harmonic motion. Till we not studied about the simple harmonic motion of this type of system where the particles have different masses and they are attached with the spring constant, with the springs of different spring constants. Now we will find the normal frequency modes. This is not the normal frequency mode where the particle one particle is in rest and other is in the motion. Now we will discuss about the normal frequency modes. If the particle is showing simple harmonic motion, then according to the resultant, the x should be equal to a cos omega t plus phi. It means we can represent the simple harmonic motion like that, where where x is given by a cos omega t, where x is equal to a cos omega t, where a is the amplitude of the motion and omega is the angular frequency and phi is the phase or the angle at t is equal to 0 time the particle displacement is shown by phi. Similarly, if the system is representing simple harmonic motion, then y can be represented as b cos omega t plus phi in this condition. If x is equal to represent by a cos omega t plus phi and y can be represented by b cos omega t plus phi, then what is x double dot and y double dot? We very well know that in simple harmonic case, x double dot, that the acceleration is equal to minus omega square x, that is displacement. Similarly, y double dot, the acceleration of the second across y displacement can be given as minus y square minus omega square y. Substituting these equation in the previous equation where we put the value of x double dot and y double dot, in our case we already obtained the value in equation number 8 and equation number 9. We are representing the equation with the help of x double dot and y double dot. If we put this value minus omega square x and minus omega square y here, instead of x double dot and y double dot, what will we have? We will get the equation a11 minus omega square x after rearranging the terms plus a12y is equal to 0. Similarly, from the eighth equation we will get a21 times of x plus a22 minus omega square y is equal to 0, where this term is representing the coordinate of x and this term a12 is representing the coordinate of y. Similarly, in the second equation, a21 is representing the coordinate of x and a22 minus omega square is representing the coordinate of y. By equation number, suppose this is 9, this is 10, we can put the find out the value of y and x. The ratio of y and x from equation number 9, we will have omega square minus a11 divided by a12. Similarly, from equation number 10 also, we will have y upon x is equal to that is a21 divided by omega square minus a22. This whole calculation is uh, taking into consideration that our system is in simple harmonic motion. It means the particle A and B having masses ma and mb, when they are displaced with the displacement of psi A and psi B, or x or y in this case, they will give simple harmonic motion only when the displacement y upon x is equal to omega square minus a11 divided by a12, or the second simple harmonic motion is possible for the same case when y upon x is equal to a21 divided by omega square minus a22, where a21 and a22 both are representing the constants, and these constants are in the terms of k1, k2, k3, and under root ma and under root mb, which we already discussed. By just evaluating these two equations, let us consider this is your equation number 11 and equation number 12. Both the equations are representing the same ratio y upon x. We will find out omega square minus a11 divided by a12 is equal to a21 divided by omega square minus a22. Just equate these two equations, and after cross multiplying this equation, we will have rearranging also with negative sign with the a11 and a22. We will get a11 minus omega square, a22 minus omega square, minus a21 a12 is equal to 0, and this is nothing else, it is a quadratic equation in omega square. This same equation which can be obtained by considering equation number 9 and equation number 10 in the matrices form. If we take this element a11, this element a12, this element a21, and this element a22, we will have a matrices, and if we find the determinant, we will get the same determinant as we have obtained from this equation. This equation can be obtained by taking the equation number 9 and 10 in the matrices form also. As this equation is a quadratic equation in omega square, so we can solve this equation with the help of our quadratic root solution. And according to that, if we have any equation in the terms of x square ax square plus bx plus c is equal to 0, then we know that x can be written as minus b minus plus under root b square minus 4ac divided by 2a. This is the general solution of this kind of equation. Similarly, we can put this solution to this equation also. By just multiplying this equation, we will find out the equation, quadratic equation of omega square, and what we will get by just multiplying these two brackets, we will have omega raised to power 4 minus a11 plus a22 omega square plus a11 minus a22 minus a21 a12 is equal to 0. This is our quadratic equation, and in this particular quadratic equation, the value of a is 1, this is the value of b, and this is the value of c. If you put all these values in this above equation, we will get two solutions for omega square. One is for negative sign and another is for positive sign. And what are the solutions? We can put this solution directly. First solution, we are indicating it with omega 1. And what is the value of omega 1 square? It is equal to half of a11 plus a22 minus 1 by 2, and this is a11 minus a22 whole square plus 4 times of a12 a21. This is the whole solution for the first root of our omega square a21, and the bracket is closed and raised to power 1 by 2. Similarly, we will get the second solution. In second solution, instead of this negative sign, we will get a positive sign. And what will be the solution? The solution is the second root of omega square, and just we will write down the same equation, but the difference is that here this term is negative, this term is positive, and this whole term goes same as the previous one, 4a1 2a21 and whole bracket as raised to power 1 by 2. These are the two simple harmonic oscillatory frequencies for our given system. Now, what should be the shape or what type of the motion shown by our system? The motion or the shape of the motion can be traced with the help of our psi A and psi B displacement. And now these both displacements are given with the help of y and x ratio, and y and x ratio and also replaced in our simple harmonic motion with their amplitude, that is b and a. It means if we want to represent the type of displacement our simple harmonic motion of the given system is showing, then we can this can be shown with the help of A and B. Let us consider the first type of motion shown by our system, that is the first mode, and it can be given in the terms of b and a. Y corresponds to b and x corresponds to a, and if this is the first mode, we can put this is the amplitude of our first particle displacement, and this is the amplitude of our second particle. And from the relation omega square minus a11, that is our equation number 11 and 12, we can find out these two values. From equation number 11, we can put y upon x is equal to b1 upon a1, when the omega square, that is angular frequency, is the first mode, that is omega 1 square, that is the first root of our quadratic equation. We will substitute omega 1 instead of omega square when we have to find the first type of simple harmonic motion. Similarly, here also for the first type of motion, that is b1 divided by a1, that equation will become a21 and this will become omega 1 square. So these are the two types of our equation which we can obtain, or there are only two variables or two type of simple harmonic motion shown by our system, like that b1 upon a1 should be equal to omega 1 square minus a11 a12, or we can say that this is equal to a21 omega 1 square minus a22 by using equation number 11 and equation number 12. Similarly, for the second mode, what type of motion can be shown with by our sec particles 1 and 2? First motion is this one, and second motion is represented with the help of b2 and a2 amplitude. Here we will using the second root of our omega square. It means there are two frequencies, and hence there are two type of simple harmonic motions possible, and here we will replace omega 1 by omega 2, and from this relation we will get when omega 1 is replaced from when omega 1 is replaced with omega 2, we will get this equation. Similarly, from equation number 12, we will get a21 divided by omega 2 square minus omega minus a22. These are our two type of simple harmonic motions which are only possible for our given system. Now, if there are two type of motion, it means we can represent with the help of different equation for x and y. For x1, That is the first mode, first type of simple harmonic motion, first shown by the first particle. We can represent this with the help of this simple harmonic equation. Second particle motion can be represented like this when the particle is moving with the angular velocity omega 1, and if the particles are moving with angular velocity omega 2, we can change the equimotion for the first particle as x2 is equal to a2 cos of omega 2t plus phi 2. For second type of angular velocity particle, we show different amplitude, and similarly, the second particle will also give an amplitude of B2 when it is moving with an angular frequency of omega 2. These are the equations for the first particle when it is moving with an omega 1 velocity, and this is for the second particle which is moving with an angular velocity of omega 1. Similarly, this is the motion of the first particle when it is moving with an angular velocity of omega 2, which is possible in simple harmonic motion in our case, and similarly this is the uh, second particle motion when it is moving with an angular velocity of omega 2. The generalized solution of our problem or of our condition or of our system can be given in the terms of x1 and x2. The first particle's motion can be given like x1 plus x2. Just put the value of x1 and x2 from the above equation. Similarly, for the second particle, only two motions are possible, and for second particle we can represent the motion like that y1 plus y2. And here the unknown factors in the above four equations are a1, a2 and phi 1, phi 2. Because only these factors are unknown, if we know a1 we can easily find out b1 by using our above expression. Similarly, if we know a2 we can easily find out the motion of the second particle if we know in which mode first simple harmonic motion is shown by the system or second simple harmonic motion is shown by the system. In our next lecture we will discuss about the energy change or exchange in between these two particles A and B when they are in motion and when they are in simple harmonic motion with each other.